Alrighty. Welcome to Specifying the Negative in TDD, part of the series of presentations brought to you by the Disciplined Agile Initiative of the Project Management Institute. My name is Scott Bain, and I've been in the software development business for well over 4 decades. Much of that was working for television and radio for CBS in California. So for many of the presentations, I tend, to some degree, to draw on personal experiences of mine from the broadcasting business to provide real-world examples of the patterns, principles, practices, and qualities that I'm trying to promote. For this one, however, I'm going to focus more on a concept than on a specific example. I want to address a question that comes up a lot when I teach test-driven development, which is, how do you write a test for something the system does not do and must not do? Science tells us you cannot prove a negative. Some say that's a fallacy. I guess a lot of people think you can prove anything, so maybe that's wrong-headed. Either way, I want to address this question in the context of test-driven development. Start. Well, one of my mentors is Jerry Weinberg, who wrote The Secrets of Consulting, and he says, always start with a joke. I have one for you from a logic professor I had in college. Tacos do not exist. We start with a known. Tangent equals sine divided by cosine. That's axiomatic at this point in history. We can factor out the n's and also the s's, leaving TA equals I over CO. Multiply both sides by CO, and you get taco equals I, or imaginary. Tacos do not exist. My logic professor was a fun guy. To get more serious, I want to examine the work of Karl Popper in his book, The Logic of Scientific Discovery, in which he puts forward the principle of falsifiability. Popper was more interested in understanding science than in doing it. And he was very skeptical about things that had recently been proposed for him, such as quantum mechanics and the discovery of the neutron. I can only guess what his reaction would be to string theory. Anyway, note how he ends this definition. A hypothesis can be refuted if it can be tested in a way executed with existing technologies. He wrote this in 1934, but we can apply this idea to what we do in test-driven development. Or can we? Test-driven development is a process of defining or specifying behavior before the code that implements that behavior is actually created. Why that's a good thing is a topic for another presentation, but for our purposes here, let's assume that this is agreed upon. TDD tests specify behavior. The majority of the time, we're creating behavior to serve a business need as defined by a customer, sponsor, or any of the many stakeholders that define and prioritize the requirements that drive development. Our hypothesis is that we meet those requirements in the code we develop, and the test is meant to prove this in a way that is entirely falsifiable, which is one reason we always start with a failing test. But there are times when such a stakeholder will define a behavior that the system should not have, and that should never be added to the system later. I think of them as the don'ts. The question I want to address here is, if we specify behavior using tests, how can we specify something negative like this? And following Popper's suggestion, how can we prove that something does not happen in a way that we know the test can fail? A test that cannot fail or cannot be executed at all does not have any validity. I want to break this must not do kind of requirement into categories, which I call the graph of negatives. Some things are simply impossible by their nature. Other things are inherently possible. Some of the inherently impossible things can be made possible by an action we might take. Others cannot, no matter what we do. Some of the inherently possible things can be made impossible if we choose to make them so. Others cannot, again, no matter what we do. Let's start with the inherently impossible things. Some things are inherently impossible depending on the technology being used. Some of these things cannot be made possible. For example, you cannot write to a CD-ROM or to read-only memory. That's in the nature of the hardware and thus does not require a specification or a test, since that would be a test that could never fail. Another example, in certain languages like C#, C++, Java, there exists the concept of private, and we know that an attempt to read or write a private value from outside a class will not compile, and so will never exist in the executable system. A test that attempted to write a private field, similarly, would not compile, and therefore would not be used, could not be used, to falsify the attempt. So some things are inherently impossible and cannot be made possible even accidentally. However, other things which are impossible by nature can be made possible if desired. It can also be made possible by accident or due to a misunderstanding of the requirements. A good example of this is an immutable object. Part of our hypothesis is that we do, in fact, understand requirements. And then in a sense, we write tests to reflect this understanding. But they do so by asserting. And the very word assert means declare that this is so, not find out if this is so. Here's a very simple example of this. Let's say your customer is an online store of some kind, and they want you to create an object that will capture a sale amount. Initially, the requirement is extremely simple. The value of any sale should be retrievable with complete accuracy on demand. This is a positive requirement that could easily be represented by a test, either an acceptance test written in business language or a unit test written in code. Which you would choose and why is an interesting topic, but let's say here that it could be either. Acceptance tests can be written in many ways, but one popular one comes from Dan North's behavior-driven development. That would work like this. Given sale amount S exists with value V, when the value of S is requested, then V is returned. Given, when, then is the fundamental language of behavior, rooted in the concept of cause and effect. We begin to understand this as little children and depend on it. Imagine a world without cause and effect. That'd be pretty terrifying. So this language expresses that observation, but it can be expressed in other ways, like this. This is a unit test written in a unit testing framework. I picked JUnit in this case, but that's arbitrary. This is the given, that a sale amount exists with a known value. This is the when, retrieving that amount using, in this case, a get method. This is the then, asserting the accuracy of the amount, including sense. Notice the use of the variable named sum amount. This is used to make it clear that the behavior is not specific to $10, but we had to choose something because unit tests are very literal. Naming test variables like this can make the test easier to read and understand, again, as a specification. Basically, we're saying ignore the specific value. It works the same for any amount. This specifies the same behavior that the acceptance test did, but it's really only readable to people who can read code. This won't compile, of course. The type itself, the constructor we're using, and the method we are calling does not presently exist. This would drive the development of a stubbed out sale amount class that does not really do much. It satisfies the compiler, but not the test. This is an important step in TDD. Might seem like busy work, but we do it because we want to observe the test failing. If the reason for that is not obvious to you, I'll just note that it's very possible to write a test that cannot fail, or that fails for the wrong reason, simply by making any number of errors when writing the test. This helps to ensure that such mistakes are not made. We have proven the validity of the test by showing Popper's falsifiability. This would cause sale amount to be changed to actually store and emit the value. Such a class might exist to restrict or validate or perfect the value it holds. It's doing none of those things now because we're focusing on one requirement at a time. This is a very basic view of the TDD process. Some people refer to this as the red bar, green bar pulse. Some implementation decisions are purely technical and should be changeable if the developer discovers a better way or a more efficient way of creating the desired behavior. but some are mandated by the customer or other stakeholder. For example, a behavior may be required by a government or other regulator. Otherwise, we would be in violation. So let's say our customer in this e-commerce application says the following. Given a sale amount S exists with value V, then you cannot change that value. Note that there is no when. This should always be true no matter what. Perhaps this is crucial for security reasons or to preserve the integrity of their business transactions. This is what is meant by an immutable object. You might even think that there's no point in specifying this, and if this was something a developer decided for technical reasons and was something that could be changed without violating the customer's requirements, you'd be right. But this came from the customer for their reasons, and we need to record to a future developer that this must not be violated. If the value is private, you can't write it from elsewhere in the system. If you try, it won't compile. But someone could make it changeable later by adding a method like setValue to the class. The customer is saying this must never happen, but we all know a future developer could completely innocently add such a method due to a misunderstanding. If we think of this from the testing point of view, we run into a problem, which again comes from the falsifiability principle. You cannot prove a negative. Well, if you can't prove a negative, how can you test for one? Therefore, how can you specify one? Software essentially is a verb. It's a does, not an is, because software only has value while it's running and being used in some way. This is one way software engineering is different from physical engineering. One could claim, at least in theory, that a beautiful bridge built across a river has aesthetic value even if nobody ever uses it to cross the river. Software which is never used is worthless and can scarcely be said to even exist. The thing it does must have business value, or we have wasted resources in creating it. But the value here, the business value, is the transactional integrity or security or whatever it is that the customer wants and will have if the set behavior is absent, not present. How can a test show this? How can it show that a method does not exist? If it tries to call the method, it won't compile and therefore cannot execute. It has to be able to do both to be part of the test suite and therefore part of our executable specification. I pose this question to students all the time if they don't bring it up on their own, which they often do. The two most frequent answers I get are, 1, just add the method so the test can call it, but have the method throw an exception or something like that. That makes it a positive behavior, and we know how to write tests about things the system does. Or use reflection to have the have the test search for the set method in the system and fail if it finds it. The problem with option 1 is that we're basically making up things on our own. The customer did not ask for an exception here. They want the action to not be possible at all. Those are not the same thing. We're not supposed to make up our own business rules to reflect the needs and values of the stakeholders. Also, if it's not really part of the genuine specification, then other developers or other teams will not be expecting this throw behavior and will not account for it. The problem with option 2 is threefold. First, reflection is not always available to us. Not all technologies offer it. Even when it is available, reflection is way too slow for TDD. TDD tests should be kept as fast as possible, so we'll run them frequently. Also, what will the test look for to ensure it's not there? Set value, change value, put value, alter value, make value. There's no end to this. What about modify value? I'm sure you can think of others. The key to solving this is in reminding ourselves once again that TDD is not initially about testing, but about creating a specification. Developers have always worked from some form of specification. It's just that the form is usually some kind of document. So think about the traditional specification, the one you're likely more familiar with. There are some very old rules associated with such a record of behavior. 1, specifications must be complete. There must be nothing that the system does that is not in the spec. 2, given rule number 1, then any behavior not specified does not exist. Ask yourself this: does a traditional specification usually indicate everything the system does not do? Obviously not. That would create a document of infinite length. Every system does a finite set of things, and then there is an infinite set of things it does not do. If the specification is complete and no ability to change the value is shown in it, then that ability does not exist in the system. That's the theory of specification. Okay, but we need it to be more than a theory. In test-driven development, tests are always written first. They reflect the requirement, not the solution, since at that point there is no solution. Production code is written to satisfy the test. No code is written except to make a failing test pass, ever. Also, it's only the code needed for that specific test to pass. So ask yourself the following question. If we were using the TDD process to create this sale amount object, and if the object had a method allowing the value to be changed, set value or whatever, how would it have gotten there? Where is the test that drove that mechanism into existence? You won't find it because there's a specific requirement that it not be there. If a developer on a test-driven team writes code without a failing test to drive it, we consider this malicious, a kind of attack. It's not a simple mistake. It's a refusal by that individual to follow the process that the team has agreed upon. The only way to prevent this is to not do it. You have to follow the TDD process diligently, or quite frankly, it will not work. But do you know any process that works if you don't follow it? I don't. Now let's talk about the things which are, of their nature, inherently possible. There are some things in this category that we can make impossible, basically prevent from happening, and then there are things that we simply cannot. When we talked about inherently impossible, we said that this can be dependent on the technology we use. JavaScript, for example, has no concept of a field being made private. And so in such a language, all fields are inherently possible to change. But even in a language that has these idioms, not every undesirable thing can be prevented. Some of them can be covered by automated tests, but some of them cannot. To make that clear, we'll need to discuss the distinction and the difference between defect detection and defect prevention. But let's start with the technology issues. Well, maybe we should choose another programming language or framework or ecosystem. Sometimes the customer doesn't care, but we shouldn't assume that. Is there a reason you want this done in PHP, my customer? Some problems will require more traditional protections, like a code review or traditional after development testing or quality assurance. TDD does not eliminate the need for such things. We must still do them. TDD is a development process, but it does not replace traditional testing, nor does it mean we don't have to do good reviews. Now let's talk about the difference between detecting defects and preventing them. There are notable times throughout a developer's day when a defect can either be detected and or prevented. For example, there is coding time. Modern IDEs will often color code problem areas or even present valid options for the coding process. As these tools get better, we find out earlier about mistakes we've made or even ways to avoid mistakes in the first place. If, for example, you declare a variable in the early part of a method, then when you hit the closed curly brace, the IDE underlines it in yellow or something, that's the tool telling you you never used that variable at all, which obviously you intended to. Or if you type the name of a reference and hit the dot, a list of public methods and fields should appear. If it does not, something is wrong. Don't proceed. If it does, you can select something that you know will be legitimate and isn't a typo or something. I really wish these tools had existed when I was a young developer. I had to write code in a dumb text editor. There's compile time. The compiler, of course, will complain things if things are not right. Again, an early part of the process that protects us from mistakes. The better the IDEs get, the earlier this happens too. There's link time. The linker can resolve external dependencies, making sure they are available, that they're the right versions, and so forth. Today, this process is mostly invisible to us unless there's a problem. Back in the day, you had to invoke this yourself. There's load time. When the system loads, there are confirmation checks we can establish to ensure that preconditions are met, that the environment is properly prepared for the system to execute successfully, and so forth. Also, in a language with generics or templates, there can be constraints that are enforced by the runtime environment. And then there's test time. The tests we write can alert us to problems, or if we write them early enough, prevent problems in the first place. In TDD, we put them first for a reason. If a defect gets past test time, then what? People ask me all the time, does everything really have to be tested? I recently wrote a rather long blog about this, but the short answer is that's the wrong question. Everything will be tested. The question is, by whom? It's either you or someone else, and that someone else will either be a tester in your company doing QA, or your customer when they use the software. I would prefer it to be me, but that's how I roll. For example, let's say we create a method that allows you to schedule a day off from work. It takes the day of the week as a parameter. If you were to use an integer where 1 is Monday, 2 is Tuesday, and so forth, then you'd have to write code in the method that would check to make sure the day passed in is not less than 1 nor more than 7, and do something if the rule is violated. It could throw an exception, or change the value to bring it in range, or calculate the modulus, or something else. That would be detection because it cannot be prevented. The IDE and compiler will see any integer as a valid input to this method. Whatever was determined to be the right thing to do if an invalid integer is passed in becomes a behavior of the system and must have a test. You would test drive that normally. If, on the other hand, you used an enumeration, which again the technology would have to provide, then the compiler will complain if someone passes in an invalid member of this set. If someone tried to pass in DOW.January, for instance, you don't have to do anything because the defect is prevented. Of course, by prevented, I mean prevented from getting into the delivered system. If it won't compile or the linker will complain or anything like that, we consider the defect prevented. We don't write tests for things that the computer can prevent for us. To examine the implications of this distinction, let's go back to the e-commerce example. The customer calls us in because they have a new requirement. They say, no sale amount over a given maximum makes any sense. Nobody's going to spend $1 million on my online store. If that happens, either we're being hacked or something has gone seriously wrong. Well, what will our code allow for at this point? Sale amount needs some kind of internal representation of the amount itself. Here, we used a double precision number to allow for dollars and cents. What's the inherent maximum of a double? In a technology like Java or C#, we will allow for a big unrealistic number, and the compiler will say nothing about it. Well, maybe we use the wrong type. What is the maximum the customer wants? I doubt it is this. But what is it? Well, we have to ask. We always have to ask. We don't make up our own business rules. So here's that conversation. Customer, you said any sale amount over a maximum is not credible and represents some kind of problem to you. What is the maximum? They say anything over $1,000 is ridiculous. Probably a hacker or a really bad calculation somewhere. Is that enough of an answer? We know what 1,000 is. What is meant by over? So we probe for a bit more specifics. How much over? Penny, $1, $10? Customer says a penny. So now we know. But C#, for example, does not have a type that is limited to 1,000 exactly. So we have to ask even more. Okay, our technology can't prevent that, but we can detect it. What should we do if that happens? We could do a lot of things. We could lower it to 1,000, for example. The customer says, raise an alarm. Make sure we know about it so we can do something. When we say everything in the system must have a test, we mean that. Even constant values are driven by tests. The given and when here are pretty meaningless. Given is just the existence of the system, and there is no when. These are static, unchanging values. But this would drive the two constants we need into existence. A QA person would probably say, you don't need to test that. Constants are inherently type safe. I get that. But this is not testing. This is specification. And the conversation we just had with our customer needs to get into the spec somehow. Otherwise, it is incomplete. It could also be a unit test. Does this seem silly to you? Well, okay. But first, can we all agree this is not a tremendous amount of work? A line or two of code, really. So what does it do? What value does it bring? It means that if the customer ever changes their mind, we can test drive the change. Imagine they say, oh, I forgot about our rare book section. If a customer bought 2 or 3 of those, that could easily be over $1,000. Let's change the maximum to $10,000. I would change the test first, watch it fail, then change the constant in production. This ensures that your tests and code are always in sync with each other. And that turns out to be immensely important when the test suite grows large, gets old. Again, you have to follow the process for it to work. This includes test driving all changes to the system. Without this test, as trivial as it might seem, you can't. This drives the constants into existence. But again, we want the test to fail initially, so they are given temporary incorrect values. So everything compiles, but the test fails. This drives the constants to their correct values. We still need to add the behavior of raising an alarm. We have to test drive that too, of course. Let's say the alarm will be an exception being thrown by the code if the amount is over the maximum. That's how we'll satisfy this requirement. There are other ways, but this is a reasonable candidate. Of course, we make sure this works for the customer too. But again, we always start with the test. Given amount S greater than or equal to maximum plus tolerance, when an attempt is made to create a sale amount with value X, an exception is thrown. Positive requirement, easy to express. Bit of a side note. Maximum and tolerance are defined in other tests, so we don't redefine them here as 1,001 cent. We use them as defined elsewhere. This prevents redundancies and lowers coupling in the test suite. These are very important things to attend to as the test suite grows large. And again, without those other tests, we would not be able to do so. In a unit test, just as easy. Some test frameworks have other built-in ways to specify exceptions, but this one will work with any of them, and I prefer techniques that travel. Your mileage may vary. Here, I'm attempting to make a sale amount that violates the rule, showing that an exception is thrown, and even which kind, all in the spec now. Of course, it fails. We have not done the work yet, but that's what we want. Also, note that the framework allows us to create a useful message when the test fails. That can be really helpful down the line. Once again, all behavior is driven by tests. We add the validation mechanism, and we integrate it into the existing code. That causes the test to pass, and therefore we have successfully detected the defect and dealt with it. We've turned a negative into a positive behavior in this case. When you can do that, the TDD approach is quite straightforward if you know all the little tricks of the trade. So let's see where we are and form some conclusions. Specifying the negative in TDD starts with identifying where that negative lives on the graph. What you do depends on that. Inherently impossible and cannot be made possible, nothing to do. It's done. Inherently impossible and can be made possible, follow the TDD process diligently. It will protect you from mistakes. Remember to think of your test suite as your specification and apply all the rules of good specifications to it. Inherently possible cannot be made impossible. Consider a switch to another technology. or do more traditional testing and static reviews. Remember, TDD does not exist in a vacuum. You should still be doing good design and code reviews, and QA should still be applied after we think we have finished and everything works. TDD does not replace these processes. Inherently possible, but could be made impossible, determine the prevent versus detect question and what the answer is. Preventable, just do it. Detectable, ask for the customer's desired behavior and test drive it into it. So if you're interested in TDD, my blog writings may be useful to you. I don't do Facebook or Instagram or Twitter or any of that stuff, but I'm on LinkedIn and I accept all connections there. I also write a lot of articles on that platform about TDD design patterns, all sorts of tech stuff. Also, if you sign up for a free account at projectmanagement.com, you can connect with me there and read all my blogs and gain access to recorded webinars I've done there. If you're interested in the training I do, all the details are there too, or you can just ask me. I do a lot of training through PMI in topics like this. Okay, so that's basically what I had for you today. Appreciate your time. If there's anything about this that you want to talk about after the fact, you can always email me at scott.bain@pmi.org, but I'm also happy to take questions and comments right now if you have any.
Yeah, so folks, I've opened it up. Just go ahead and ask away. And thank you, Scott. Very good presentation. Matter of fact, I'm sending this to my team soon.
Excellent, wonderful.
Okay, questions, comments, general discussion.
Unbridled praise. Well, I guess I did a perfect job. No one has any questions.
Okay.
Yeah, sure. Do you have a preferred testing framework that you prefer to use?
For unit testing or acceptance testing?
For unit testing?
Well, I mean, it depends on the language you're developing. And I always like to stick in the language of development just so you're not context switching. You're going
Correct.
between the tests. Yeah. So depending on the language you're developing in, like if it's C#, personally, I like MS Test. A lot of other people prefer NUnit. If it's C++, I like CXX test because you don't have to intertwine a lot of testing stuff in your production code. Java, obviously, JUnit. I like RSpec for Ruby. But yeah, it kind of depends on the language you're developing. When it comes to acceptance tests, it kind of depends on what acceptance testing language your stakeholders prefer. The given and when then thing is just one way to do it. There's a whole bunch of other ways. And the acceptance testing automation tools, each one is like better given the form of expression. So I usually let the stakeholders kind of figure out how they want to talk about acceptance, then pick the tool. Anybody else? Well, if you think of something later, again, that's scott.bain@pmi.org. I'm also on LinkedIn. I do a lot of writing there. And you can go to projectmanagement.org and link up with me there if you prefer that. I do a lot of presentations for them too, and they all get recorded. So once you have an account there, it's free. You can watch them all. So probably will do this one for PMI as well. This is the first time I did this one, actually. I created it for you guys.
Thank you. You've given me a lot to think about without any specific questions at the moment.
No problem. It's kind of an unusual, so I wasn't sure we'd get a lot of questions right.
Yeah, so from my side, I'm actually in aerospace, and guaranteeing certain things do not happen is actually a major area that you kind of need to look at. And it's one that's not well understood, I think. It's yeah. So this was very valuable.
The company that asked me this, that caused me to create the graph of negatives, was a medical company, and they're very similar in that way.
Yep.
They're just thinking it can't happen. Yeah, so that graph of negatives came out of that consulting session. All right, well, I guess that's that, Lloyd. I'll let people go, I suppose. Yeah.
Awesome. Thank you very much, folks.
Yeah.
Oh, another question?
Well, I was just going to say, when I was working in aerospace and we were turning on a new antenna for the first time, they asked people to make sure that they were wearing clean underwear. So maybe it would have been better to have some tests.
I think that's probably true with MRI machines too. If you've ever been around one.
We're doing rocket engines, and I haven't heard that one yet, so it might be a good idea.
That's very good, very good.
Okay, thank you, everyone. I've got a speaker lined up for next month, so I'll be announcing that toward the end of the month. Thank you for presenting, Scott. This was wonderful.
My pleasure.
And we'll get the video and slides posted the next day or so.
Excellent. Thank you.
Okay. Thank you, everyone, and good night.
Have a good evening, everyone.
All right.
Talk to you next time.